Scientists who are members of the Division of Chemical Physics work on projects which have complicated names. The papers they publish are full of elaborate mathematics. Most laymen would have trouble guessing whether their work was of any use or not, and not only the layman.
When I got the thing set up and it was giving the sort of results I expected, I was terribly excited. And I called in one or two of my colleagues and I said, look, that's atomic absorption. And they said, well, so what?
In 1952, the apparatus which left Dr. Walsh's colleagues so unimpressed seemed just an intricate scientific toy. Today, it has created an industry. This is the modern instrument. Aim, to determine the amount of copper present in the sample. The result? Just over a half a part per million. Time of analysis? Less than 2 minutes. The technique is called atomic absorption spectroscopy, a technique which in the space of a few years has become one of the analytical chemist's most powerful tools.
We use atomic absorption analysis in the study of nutrition of plants and animals in a wide variety of experiments.
We use atomic absorption spectrophotometry in this hospital for measuring the amounts of elements which are normally present in very small amounts in the bodies of infants and children.
We used atomic absorption firstly in 1962 to test for iron and copper in wine.
We used atomic absorption for the determination of metallic impurities in plating solutions.
We are using it for the routine testing of diesel engine lubricating oils.
If applications for the method have grown by leaps and bounds, the idea itself, in its day, seemed to grow almost casually. Dr. Ellen Walsh was its chief pioneer.
In the early 1950s, our spectroscopy group, which consisted of 4 people, was concerned almost entirely with studying the way small molecules absorb radiation of different wavelengths. We also had a minor interest in studying the way atoms emit radiation. And the reason we studied the way atoms emitted radiation rather than the way they absorbed radiation is that this had been the technique that was almost invariably used and had been since the early experiments of Bunsen and Kirchhoff in 1860.
During the early part of the 19th century, it was customary to identify chemical elements by observing their emission spectra. 2 German scientists, Gustav Kirchhoff and his colleague Robert Bunsen, described the method in 1860.
It is well known that certain substances possess the property of imparting definite colors to flames in which they are heated. When the colored light thus produced is analyzed by a prism, spectra exhibiting differently colored bands or lines of light are seen. Upon the occurrence of these lines of light, an entirely new method of qualitative chemical analysis can be based, a method which greatly enlarges the scope of chemical reactions and points to the solutions of problems hitherto unapproachable.
Elements could be identified by their emission spectra, the characteristic wavelengths of light which they gave off when heated. But Bunsen found, by passing a light through the flame, that the heated vapor of the element could also absorb light of its own particular wavelength, causing it to disappear from the continuous spectrum of the light source. He first observed the phenomenon with sodium chloride. The emission spectrum, and then the absorption spectrum. The yellow sodium line was missing. Clearly, the sodium atoms in the flame were absorbing light at their own characteristic wavelength. The discovery of the absorbing powers of atomic vapors provided an explanation for the dark lines which had been observed in the solar spectrum some years before. Some of the radiation coming from the extremely hot center of the sun was being absorbed by atomic vapors in the relatively cooler outer layers of its atmosphere.
Hence, in order to effect the chemical analysis of the solar atmosphere, all that we require is to discover those substances which, when brought into the flame, produce bright lines coinciding with the dark ones of the solar spectrum.
This first application of atomic absorption was certainly very spectacular. Elements had been identified on the distant sun. But the early scientists looked upon it only as an alternative to the apparently simpler method of emission. In the next year, Bunsen and Kirchhoff discovered two new elements, cesium and rubidium, by observing their emission spectra, and for the next 100 years atomic absorption was to take second place.
I think the point is that all spectroscopists, and certainly including me, had always felt that since atomic emission spectra and atomic absorption spectra gave very much the same type of information, one tended to think only in terms of atomic emission spectra because they were very much easier to record. And nobody looked carefully into what the underlying properties of atomic absorption spectra were compared with atomic emission spectra. I think the reason I had the good fortune to look into this question a bit further was largely the result of my own personal experiences in spectroscopy, in that I'd spent the first 6 years of my professional life studying the way atoms emit radiation, and I'd studied for the next 6 years the way molecules absorb radiation. And it was almost a natural question that at some stage I should say, why don't we also consider the way atoms absorb radiation as well as molecules? I calculated how much absorption you would get if you pass light through the atomic vapors of various elements at various temperatures. And the surprising thing was that one found that the absorption was independent of temperature, and it was also of very much the same order of magnitude from one element to the next. And in this sense, it was completely different to atomic emission measurements. And in particular, it was quite obvious that if you could make atomic absorption measurements, in many cases you would get very much greater sensitivity than you could ever get with emission measurements.
Such findings, it seemed to Dr. Walsh, would be of great interest to all chemical analysts, and he looked forward to hearing their reaction to his theoretical paper, which was published in Spectrochemical Acta in 1955.
I was terribly disappointed at that time when I couldn't interest any spectroscopist in what I proposed to do, with the exception of the director of research of one of England's leading instrument companies. And he was terribly excited by the arguments I was putting forward. He came to visit us in March 1954 to see our equipment, which we then were exhibiting at the Institute of Physics exhibition in Melbourne. This was an incredibly complicated-looking bit of equipment, although terribly simple in principle.
The solution to be analyzed is sprayed into a flame, which converts it into an atomic vapor. By passing light of a selected wavelength through the flame, the absorbing power of this vapor can be measured. The amount of absorption varies over a narrow band of wavelengths. It is the peak absorption value only which is proportional to the concentration of atoms in the flame. In order to get an accurate measurement of this peak absorption value, a special type of atomic spectral lamp, known as a hollow cathode tube, is used as a light source. This is designed to emit a modulated or pulsed signal consisting of several very narrow spectral lines, which are characteristic of the element being determined. When the atoms are sprayed into the flame, they absorb light of their own characteristic wavelength. That is, they absorb one of the spectral lines emitted by the hollow cathode tube. This line is much sharper than the absorption profile of the atoms in the flame, and this makes it possible to measure the peak absorption value accurately. The method needs only a simple monochromator to isolate the required line for measurement. A tuned photoelectric detector records only the pulsed signals from the light source, but rejects signals from the flame which are not modulated.
And it created no interest whatsoever. And this is the type of lack of reaction that we experienced for the next few years. And after we published our early papers in 1955, 56 and 57, we found very little encouragement in the reaction from spectroscopists overseas.
But there were some alert minds who saw possibilities for the new method. First off the mark were two agricultural chemists. One of them, at the Ruakura Soil Research Station in New Zealand, was Mr. Eric Allen.
A lot of our agricultural research work is carried out by means of field trials and pot trials on the different soil types in New Zealand. And to properly understand the results that are obtained, it's absolutely essential that the plant should be analyzed, the soil should be analyzed, and this results in an enormous analytical program. We had made a 3-channel emission flame photometer for the determination of sodium, potassium, and calcium, but we had no rapid and reliable method for the determination of magnesium, and this was a real bottleneck in putting through large numbers of samples. But when I read Ellen Walsh's first paper in 1955, this appeared to be just the thing we were looking for. We inquired about hollow cathode lamps from Hilgers and eventually obtained some from this firm in about 57. However, before getting these lamps, we were a bit impatient to find out whether this atomic absorption method, first of all, whether it really worked, and secondly, whether the sensitivity would be adequate for what we wanted. And so we did quite a bit of preliminary experimental work by recording absorption spectrograms. We satisfied ourselves that the method would certainly work, and we got a rather rough idea of what the sensitivity for magnesium and iron and manganese would be. We eventually got lamps in early 57 for magnesium, iron and manganese, and within a week or two of receiving the lamps, we were using atomic absorption for the routine analysis of plant materials and soil extracts for magnesium.
In the meantime, at CSIRO's Division of Plant Industry in Canberra, Dr. John David was also working on the new method. Today, he still uses the instrument which he assembled in 1957 after some early discussions with Ellen Walsh.
It is a relic from the early days, really, in that it was an instrument that was put together from bits and pieces, more or less. The spectrograph is a Hilger medium with the plate holder removed and a stage placed there to carry an exit slit and photomultiplier. Electronics from the Division of Chemical Physics. Originally a hollow cathode lamp from the Division of Chemical Physics, and a burner spray chamber system. The burner, incidentally, is just a squeezed down piece of stainless steel tube. It is used still in this division for the determination of sodium, potassium, calcium and magnesium in plant material and soil extracts, blood serum, in fact any agricultural sample in which it's necessary to determine these elements.
And so in round about the beginning of 1958, we had a peculiar situation in that several Australian laboratories were interested to try out our technique, but there was nobody willing to make them the apparatus. And this was when we decided that we would arrange for the manufacture of suitable bits of equipment for them to use so that they could try out the method on their particular analyses in their own laboratories. And this really is how we began local production in Australia. We arranged for 3 different small firms to make different bits. One firm made the electronics to our design. Another firm made the mechanical bits and the optical parts. And a glass-blowing firm was persuaded to make the special type of hollow cathode lamp which we had developed for making atomic absorption measurements. And between 1958 and 1962, I think we fitted out about 30 Australian laboratories with this terribly simple type of atomic absorption apparatus, what we used to call working men's equipment. And this was how the method was tested under routine conditions on real problems. And almost without exception, the people found the method entirely satisfactory, and a tremendous wave of enthusiasm was generated in Australian industry.
Our first association with Ellen Walsh came about in 1959 during a routine visit of inspection to his laboratories. It was very difficult to assemble the instrumentation which was required for carry out the technique, and it took us some 12 months to gather this instrumentation together. And at the same time we had a developing problem in trying to do large numbers of magnesium analyses which were very difficult to obtain with instrumentation which was available to us at that time. In early 1961 we were able to achieve successful magnesium analyses in cast iron and steel, and we were able to carry out work down to the level of 10 parts per million of magnesium in those materials. We realised that the technique would be applicable to a wide range of other products in our industry, and we commenced out on a large program aimed at doing analyses for copper, manganese, nickel, cobalt and chromium in iron and steel products.
Despite the growing use of atomic absorption, a further research effort was still needed to speed the method on its way. At the Division of Chemical Physics, Dr. John Willis was busy extending the range of applications.
I first got involved in atomic absorption early in 1958 when Ellen Walsh, after going to a conference in the United States, came back and said, there seems to be a considerable interest in the measurement of calcium in blood serum, and it has been suggested that atomic absorption is a possible way of tackling that problem. Would you be prepared to look at it? So I took on this assignment knowing very little about blood serum, nothing at all about atomic absorption. So it turned out to be one of the more difficult problems I could have tackled as a first effort in a new field, but in the end it was solved in a reasonably satisfactory fashion, and as a result of that one of the American companies took out a license to manufacture atomic absorption equipment. An interesting sideline, as a matter of fact, was the determination of magnesium in blood serum, which hitherto had scarcely been attempted because it was so difficult. It turned out that by using atomic absorption, magnesium could be determined very simply, very accurately, and on very small quantities of blood. And this was an interesting example of something which started out to solve one problem, actually solving a more important one on the way to get there, so to speak.
But in 1962, one of the big American instrument firms decided that they were going to enter the atomic absorption field in a big way. And similarly, in that year, the firm of Tektron Proprietary Limited in Melbourne, which had been making our electronic bits, decided that they would market a complete equipment. And from that time on, I don't think the method has suffered any serious setback.
One of the first cases in which we used atomic absorption spectrophotometry was a boy. I think he was about 7 years old. He was very badly burnt. He was in the hospital, and then suddenly, quite inexplicably, he started to convulse. We didn't know what was going on, but we tested his blood for magnesium, found the level was very low, replaced the magnesium, he stopped convulsing, and he made virtually a complete recovery. This was a very dramatic case, an early one. Since then, of course, we've used this technique for a lot in routine care in the hospital. Children with gastroenteritis, losing these elements from the bowel and so on, but also using it very much as a research tool within the Children's Medical Research Foundation.
We use atomic absorption for the determination of metallic impurities in electroplating solutions because in plating solutions they can cause detrimental effects to the final electrode deposit. For instance, in a bright cyanide copper deposit, it should be fully bright all over, but in an electrode deposit which has been contaminated with chromium, you end up with no copper deposited in this low current density area. Another example is in bright nickel plating, where the panel, again, should be fully bright all over, but a solution contaminated with, say, copper at the level of about 45 parts per million, you get this effect here in the low current density area of a dark black deposit which is brittle, highly stressed. With the instrument here, we can measure these metallic impurities in the plating solutions down to very low concentrations. We can do it quickly and accurately, and what we are measuring is in fact the metal or the metallic impurity which we are after.
Yes, we first used atomic absorption in 1962 for the purpose of determining iron and copper in wine. These metals cause clouding. Now, if we can determine the iron and copper levels and regulate that quantity, we'll be so much better off. Prior to this, we'd use wet chemistry methods involving separations, extractions, and development of colour in spectrophotometric methods. This was fine, except that it took 2 days to accomplish. We streamlined our methods and got the job down to about a half a day. Then, with the advent of atomic absorption, a test was completed in about 2 minutes. So this really meant something to us. We also used the atomic absorption for determination of lead. This in itself was a very long and protracted operation requiring 2 days. Now it is done in that same period of perhaps a couple of minutes.
We are using atomic absorption techniques for the analysis of our used lubricating oil from our diesel locomotives. These diesel engines are the power source in our locomotives, and of course it is of utmost importance that we have the information of the oil conditions. We are maintaining a constant history of the lube oil analysis figures, and any variation from the established trend gives us the indication that something is wrong with this particular unit. Now, the elements we are testing for are iron, copper, lead, silver, and chromium. The most informative one is the iron, as it gives us most useful indications of the engine conditions. Say, for instance, I increase in iron from 10 parts per million to 20 parts per million. It would definitely spell trouble.
And then came the Australian mineral boom, and with it the need for analyses on a hitherto unheard of scale. By the time the boom arrived, the analytical method was already waiting. Analyses could be carried out in the laboratory and in the field. In Australia, there are now more analyses carried out by atomic absorption than by all other methods combined.
By far the most profitable application of atomic absorption has been in geochemical assaying. The cost of analysing mineral samples for several elements, for example, has been reduced enormously. Each instrument represents a gain in productivity valued at about $200,000 per annum if it's used continuously, as many of them are.
But what is the economic gain for Australian industry as a whole? Mr. Albert Brown's cost-benefit analysis on the atomic absorption project leads to some interesting figures.
Taking the time value of money into consideration, the net benefits to date are in the order of $20 million. But looking into the foreseeable future, say about 10 years hence, these benefits will increase in value to $120 million, or maybe even up to as high as $180 million.
Such an analysis is possible because atomic absorption has reached the industrial application stage. At the time the basic studies were begun, these widespread benefits could not have been predicted, nor could anyone have foreseen that a new branch of science and technology would be created. This unpredictable quality, sometimes frustrating, sometimes exciting, is at the core of all basic uncommitted research.
I was in America in 1958 and 1960 lecturing on the subject, and it was quite obvious that there was no great interest in what we were doing. People regarded it as of academic interest, but not really of much practical utility.
Not much practical utility. That's how it seemed in 1960. Yet 10 years later, the production lines of licensees all over the world are busy. This firm in Melbourne was one of the original licensees. In 1962, while still a small electronics firm, they assembled their first atomic absorption apparatus. In 1969, they produced over 500 units, valued at $2.5 million, and exported 2/3 of them.
Charlie, could you get some? I can't, I have the door. I'll take that one off. Now I think it's all right. Oh, Charlie. Hello. Not too bad. Seems to have voice. Why? I've been talking too much. Look as if you're having a bit of trouble there. Just a little bit. I'll take this off first, all right? And then I'll put it on the expect line.
Work at the Division of Chemical Physics still goes on in harmony with an ever-increasing research effort overseas.
Good conference?
Excellent conference, yes. 400 people turned out.
Any new work on flame?
Nothing new on flame, but Professor Lvov at Leningrad is doing some really good work on furnaces now.
Well, that's good. If we ought to repeat some of that work.
I think we should do something, yes.
The conference, from which Dr. Walsh has just returned, was the first major international conference devoted entirely to atomic absorption spectroscopy.
Is that a new lamp?
Yes, they're new lamps. They show quite a significant improvement over the old times.
You seem to have got the sputtering apparatus pretty well complete.
I thought at one stage, perhaps in about 1957, that I'd finished on atomic absorption. I mean, I'd published the idea, and that seemed to me just about enough that any man should do.
Yes, this is our latest design.
it was only because, really, of the cold shoulder treatment that we were given that we got a bit mad and got involved in proving a point. So if the world had reacted differently, we might have come out of this with nothing.